Hello everyone, my name is Liu Xing. I come from China Nuclear Power Operations Company Limited. Today, my report topic is failure analysis and factors influencing spline wear in hydraulic motors or charging pumps in nuclear power plants. My report consists 5 parts. Part 1, Introduction. A charging pump is an important piece of equipment in nuclear power plants for controlling the chemistry and volume of the primary loop. These pumps employ an external oil circulation system for the lubrication and cooling of the non-drive and bearings. The oil circulation loop includes an oil cooler driven by a hydraulic motor. However, after the commissioning of charging pump assembly in this study, frequent failures and varying degrees of wear were observed in the internal splines of the hydraulic motor. Several splines completely failed during operation, leading to the loss of cooling function in the oil circuit and necessitating the shutdown of the charging pump assembly. The wear condition of each spline is not the same. Some splines wear out quickly, while others wear out slowly. This issue has adverse effects on the safe and stable operation of the nuclear power plant reactor. Figure 1a illustrates the overall structure of the charging pump assembly. Figure 1b depicts the schematic diagram of the lubrication system. Figure 1c and Figure 1d illustrates the schematic diagram of the internal and external spline wear failure. As a key component for shaft-to-shaft coupling, splines facilitate the transmission of radial motion and torque. Few studies had focused on the internal spline wear issues in the hydraulic motor or the charging pump assembly in nuclear power plants. To address these issues in this study, a detailed investigation and analysis of the charging pump in a nuclear power group was conducted. The wear pattern of the spline was confirmed through a metallographic analysis and the spline's microstructure, hardness, and chemical composition were analyzed. With the aid of finite element analysis techniques, the influence of factors such as material stress, eccentricity, and lubrication on spline wear were investigated. Part 2, investigative and analysis methods. Failure investigation process. The specific procedural sequence is planned as follows: 1 to 7. Process of material failure analysis. A microscopic morphology examination was conducted. After this microscopic scrutiny of the wall surface was undertaken. Continue the analysis and intricate investigation into the microstructure of the spline was performed. Finally, a comprehensive hardness analysis of spline was undertaken. Calculation condition of working stress of spline. For the wear analysis of spline surfaces in the hydraulic motor, this study established an altered wear model to simulate the wear behavior of the spline surfaces. In this study, the altered model was adopted for the calculations. Figure 3 shows a schematic diagram of spline transmission structure in hydraulic motor. The simulation calculations were performed using Abacus software. Fig 4 shows the computational mesh model of the spline shaft. Different levels of eccentricity within the permissible range were considered in the analysis. The torque acting on the spline shaft could be determined based on the pressure difference at the inlet and outlet of the hydraulic motor using the formula provided in the created product manual. Considering the actual operating condition of the hydraulic motor on site and a normal operating pressure differences of 35 bar, the calculated transmitted torque during normal spline operation that follow M equal 4.15 for the rated operating pressure of the hydraulic motor at 280 bar. The calculated transmitted torque through the spline is as follows: M equal 33.25. The torque of M equal 4.15 were applied to the external splines, and the internal spline rotated at a speed of 2000. This was done to analyze the forces and the wear of the spline pair. Figure 5 shows boundary conditions for spline calculation, where conditions under different lubrication conditions. Figure 6 illustrates the oil flow model for spline lubrication. Figure 7 shows lubrication of system simulation model. Part 3, result discussion. Microscopic observation of spline damage. Morphology. The photographs of spline after disassembly and inspection of hydraulic motor are as shown in Figure 8. Based on the structural characteristics of spline and this wear characteristic, it could be preliminarily inferred that the spline had experienced microslip wear. In the wear region, wear marks were observed at an angle to the axial direction and parallel to the axial direction, as shown in Figure 12A to B and D. On the surface of the worn area of inner spline, wear marks were visible at the angle to the spline axial axis and approximately parallel to the axial direction, as shown in Figure 13A to B. Figure 12 and Figure 13. The schematic diagram of sampling position is provided in Figure 14A to B, and the cross-section morphology of the samples after sampling is shown in Figure 14C to D. Figure 15 shows metallographic morphology of the external spline. Figure 16 shows a microstructure morphology of the inner spline surface. A spline hardness analysis. The average value are shown in the Table 2. Surface to core hardness measurements were conducted for both the inner and outer spline surface as shown in Figure 17, Table 2, and Figure 17. Chemical composition analysis of spline material. One sample each was obtained from the outer and inner spline surfaces for chemical composition analysis. The result are shown in the Table 3. Influence of force conditions with different eccentricities on wear. On the actual operating condition, working pressure of 35 bar, the maximum contact stress on the spline was 13.94, which was significantly lower than the maximum contact stress of CT 4.46 on the rated operating condition, working pressure of 280. Figure 18 shows contact pressure on inner and outer spline for different targets. Figure 19 shows the maximum contact stresses on different tools and faces for various eccentric distance. Where conditions with different eccentricities, the calculation of the wear depths for the inner and outer splines with different eccentricity revealed the variation of maximum wear depths over time, as shown in Figure 20. Figure 21 shows oil velocity distribution under different working pressures. Figure 22 shows comparison of lubrication oil quantity under different working pressure. Figure 23 shows variation of inner and outer spline wear depths over time under different lubrication conditions. Part 4, calculation of straight shaft hydraulic motor. The new structure hydraulic motor adopts a straight shaft structure. During the operating of the fan, the actual force generated will be directly transmitted to the gears through the direct shaft, potentially leading to wear both and faces. This report conducts finite element analysis on the straight shaft and eight-shafted key sleeves on the new structure hydraulic motor. Figure 24 shows schematic diagram of the connection structure between old and new structure hydraulic motors. Figure 25 shows schematic diagram of the evolution locations for the new and older structure assignment. The specific computational model is as shown in Figure 26. Detail of the machine can be seen in the following Figure 27. Direction, connection, structure, boundary, and friction coefficients. The friction coefficient was set to 0.05. The relevant parameters for the direct drive shaft structure calculation are shown in Table 4. Figure 28 shows force on the shaft sleeve on the fan side. Figure 29 shows force on the shaft sleeve away from the fan side. Figure 13 shows force on the at shaft key body near the fan side. Figure 31 shows force on the at shaft key body away from the fan side. From the calculation results, friction and wear between the shaft and the shaft sleeve was minimal. The calculation model is shown in the figure 32. The grid model is shown in the figure 33. The wear between these and faces can be considered negligible. Part 5. Corrective action. The nuclear power plant has conducted a trial of new straight shaft hydraulic motor. The on-site operational result showing that the straight shaft hydraulic motor had been in operating for an entire cycle of the nuclear power unit. Currently, the motor is in good condition and the efficiency of the cooler has not decreased. The main structural components are found to be in good condition with no apparent signs of wear. That's all. Thank you.